All right, let's dive right in. Today, we're talking about the very essence of, well, everything matter. You know, the literal stuff that makes up the air we breathe, the ground we walk on, even the stars in the sky. It's all around us.
So, take a second, just look around you right now. Your phone, your desk, the water you're drinking. What is all of it really made of? I mean, if you could zoom in way, way down, what would you find? It's a question people have been asking for thousands of years.
And the answer? Well, it's pretty wild. We're talking about a world that is so ridiculously small, it's almost impossible to wrap your head around. A hidden world that, get this, writes all the rules for everything we can actually see and touch.
So, first things first, let's settle a really old debate. Imagine you're holding a block of wood. Is that block one solid, continuous thing with no breaks or gaps, or is it actually made of a bajillion tiny, separate bits all stuck together?
For the longest time, this was a huge argument. You had one side saying, nope, matter is continuous, like a perfect, seamless block. And the other side argued, no way, it's got to be made of tiny, individual particles, kind of like sand. So, who was right?
Well, a super simple experiment you can do at home basically settles it. Picture this. You get a glass of water and mark the water level. Then you dump in a spoonful of salt and stir it all up until the salt completely disappears. But here's the crazy part. The water level doesn't go up. How on earth is that possible? And boom, there's our answer. The only possible explanation is that the tiny little particles of salt are actually slotting themselves into empty spaces that were already there between the particles of water. So matter isn't a solid block at all. It's made of particles, and there's space between them. And when I say tiny, I mean, wow. It's hard to even describe. Think about this. Just 2 or 3 little crystals of a substance called potassium permanganate have enough tiny particles in them to turn 1,000 liters of water bright pink. That's how small we're talking. Okay, so we've nailed it down. Everything is made of particles. So what's next? Well, now we have to figure out the rules they play by. What's the secret code that lets these tiny particles build everything from a rock to a rain cloud? It turns out it all comes down to 3 basic rules. Number 1, which we just proved, particles have space between them. Number 2, they are never, ever still. They're always moving, vibrating, zipping around. That movement is called kinetic energy. And rule number 3, they attract each other. There's a force pulling them together. Now, to get a handle on that attraction force, this is a fantastic way to think about it. Imagine the particles are like these I Do Mish Me dancers holding hands in a chain. Some are holding on for dear life, a really strong grip. Others might just be barely touching fingertips. The strength of that bond can be strong or weak, and that changes everything.
So how do these 3 simple rules, space, movement, and attraction, build the world? Well, once you get how those 3 things work together, you've cracked the code. You understand the 3 main states of matter we see every single day: solids, liquids, and gases.
This table right here is basically the cheat sheet for the whole thing. You can see in solids, the attraction is maxed out. The space is tiny, and the particles just kind of shiver in place. For gases, it's the total opposite. Almost no attraction, huge spaces, and particles going wild. And liquids, they're the happy medium right in between. Let's look at solids. Here, the particles are packed together super tight. That force of attraction is so strong, and the space between them is so small, they're basically locked into a grid. They can vibrate a little bit, but they can't go anywhere. And that's exactly why a solid is rigid and holds its own shape. Now, what about liquids? Well, here the forces are a bit weaker, and there's a little more elbow room. This means the particles can break free from their fixed spots and start to slide and tumble past one another. It's why liquids can flow and why they'll take the shape of any container you pour them into. And finally, we get to gases. In a gas, the particles have so much energy and the attraction between them is so weak, it's basically a free-for-all. They just fly off in every direction, bouncing around like crazy. They will expand to fill any space you give them, which also means you can squeeze them down really easily. They're highly compressible. Okay, so we've got the states of matter down, but here's where it gets really cool. We can actually change them. We're not just stuck with what we have. We can control this whole game and force matter to switch from one state to another. But how do we do it? It really comes down to 2 main control knobs that we can turn: temperature and pressure. By cranking up the heat, we give particles more energy to move. Or, by increasing the pressure, we can physically squeeze them closer together. These are our tools for changing states. But this brings up a really weird puzzle. Think about melting ice. If you put a thermometer in a cup of ice as it melts, the temperature will get stuck at exactly 0 degrees Celsius. It won't budge, not until every last bit of ice has turned to water, even though you're adding heat the whole time. So where is that heat energy going? The answer is this awesome concept called latent heat. The word latent just means hidden. So this is the hidden energy. It's not being used to make the particles move faster, which would raise the temperature. Instead, it's being used for one specific job, to break the bonds holding the particles together in their ice crystal structure. It's the energy of pure transformation. And you can see how this whole system is just one big cycle. Temperature and pressure are like switches. You can add heat to melt a solid into a liquid, and then boil that liquid into a gas. And you can even do weird things, like jump straight from a solid to a gas. That's a process called sublimation. It's what dry ice does.
So let's wrap up with one last amazing change of state. It's one that happens around us all the time, completely silently and without any boiling at all. I'm talking about evaporation, the great escape of particles. And you already know how this works from everyday life, right? Evaporation gets faster when you increase the surface area. That's why you spread your wet clothes out to dry instead of leaving them in a ball. It's also faster when it's hotter, when it's windy, and when the air is less humid. All of those things make it easier for particles on the surface to just take off.
And here is the real kicker, the reason this matters so much to us. Evaporation causes cooling. See, it's the fastest, most energetic, hottest particles at the surface that have enough juice to escape. And when they leave, they take all that heat energy with them, which lowers the average temperature of what's left behind. This is literally why sweating cools you down. It's your body's personal air conditioner. So, I'll leave you with this. The next time you're outside and you see a puddle slowly shrinking on a warm day, remember what's really going on. You're not just watching water dry up. You are witnessing an invisible, chaotic, and beautiful drama where trillions of individual particles are finally gaining enough energy to break their bonds and make the great escape into the air. Pretty amazing when you think about it, right?